So I'll give you a brief intro about what is remote sensing, what does it basically mean, and the components of the electromagnetic spectra, its range, different types of waves, visible rays, X-rays, microwaves, infrared, ultraviolet, etc. And some basic concepts behind it, some basic Wien's law, Stefan-Boltzmann's law, etc. All right, so we'll start with the basic idea of remote sensing. So what is remote sensing? So yesterday we discussed, when we discussed in the course introduction, I told you even our eye, a camera, a satellite, these are all remote sensing system, right? As the name suggests, you are remotely sensing data from a faraway object without actually being in contact with it, right? So you are obtaining information about an object, area, or phenomenon through analyzing that data acquired by a device which is not in contact with the object, area, or phenomenon under investigation. So that is the pretty much a more formal definition of remote sensing. So if you look at it, you can see you are obtaining data about an object, an area, or a phenomenon, and analyzing that data which was acquired by a device which was not actually in contact with that particular object, area, or phenomena, right? So basically what you're doing is you remotely collect the data, analyze and obtain that information and use it for various purposes, right? So what is this data actually? What data do you actually collect? So the data that you collect can actually be variations in force distributions, acoustic waves distributions, electromagnetic energy distributions, etc. So in this course, we will be mainly focusing on electromagnetic energy distributions. So how this whole process works? There are basically 7 steps before a user gets to use information product. So you have basically 7 steps as I mentioned. So if you are considering satellites or sensors in a camera or anything, any remote sensing sensor, they acquire data from the electromagnetic energy emitted from various earth features. Where does that energy come from? You're dealing with the energy that is emitted from the features on the earth's surface. Suppose you are taking a photo. Suppose you are taking a photo in a mobile phone, right? So you are clicking a photo. What are you actually capturing while taking a photo in your mobile phone? Reflected wavelets of visible light, isn't it? Your photo will be a combination of different shades of the basic colors, red, blue, and green, isn't it? So these various wavelengths of the electromagnetic spectra that you can see is what you perceive, isn't it? But remote sensing sensors, maybe in satellites or so, or maybe thermal scanners, etc., they can see or sense, see within quotes, okay? They can see or sense data in different wavelengths, right? Do you know what is the wavelength that a human eye can perceive? The wavelength in the electromagnetic spectra that the human eye can perceive. How many colors can we perceive? What is the wavelength of colors or wavelength in the electromagnetic spectra that we can perceive? 380 to 700 nanometers, right? So that is the only range that we can perceive. But do you think that is the only existing energy or wavelength? Do you think so, or are there more? There are many more, isn't it? There are wavelengths less than that, where there are wavelengths higher than that. So these wavelengths can be recorded by different sensors tuned for the same, for various purposes. So maybe the human eye cannot perceive these different wavelengths, but we have made sensors which can actually perceive different wavelengths. So different objects on the earth's surface emit electromagnetic energy at various wavelengths. So this can be captured by these sensors. So once you capture this, but you have to have an idea of where that location is situated, right? Maybe you might have seen in your mobile, if you take a photo, there is an option for geotagging. Have you heard of it? So Google will automatically group your photos and all based on where that photo was clicked, isn't it? Have you seen that? So that is basically you are collecting some data about an object and you're saving that data, and using the GPS you are also storing the spatial location of that particular data, lat longs of that data, maybe using the GPS, right? So this data is basically collected based on the electromagnetic energy distribution using various sensors which are airborne or spaceborne platforms. Basically, in the case of large scale remote sensing satellite data, there will be airborne or spaceborne platforms, and then the next step will be, you will be inventorying or mapping or monitoring these earth resources. That is what we basically do using this satellite remote sensing data. So as I mentioned, there are basically 7 steps. As you can see here, you can see the flow chart. Before the user gets to use that data, there are basically 7 steps. So the first one is the source of energy or the source of illumination. So where does this earth emit these energies actually? How can earth emit electromagnetic energy? How does that happen? Sun, right? Sunlight, isn't it? But you can, take photos in the dark also, isn't it? Can you take photos in the dark? You use a flash, no? Sometimes, isn't it? That's an external source of energy, right? Other than that, the most of the energy, of what we observe, the energy that is that our eye or the camera that it perceives, it is basically the reflected energy from the sun, or some of the energy will be stored by the earth features and they will be emitted at a later stage, right? This is what basically happens. So the first thing that you need is an energy source or illumination. So that is the first requirement of remote sensing, which is to have an energy source which illuminates or provides some electromagnetic energy to the target of interest. So that is the first step. So you need to have a source of energy. Then the second step is the propagation through the atmosphere. So in that, the energy, when it travels from the source to the target, it will come in contact with and interact with the atmosphere it passes through, right? So this happens once again. You can see here in the fourth step, there is a retransmission again. So this, from the source of energy, it will propagate through the atmosphere. So there is the first interaction will happen in the atmosphere, right? With the atmosphere. Then it will reach the Earth's surface features. Then it is basically retransmitted through the atmosphere, basically reflected, right? Reflected, or when that energy might be saved and then it is later emitted. So from the Earth's surface features, it is retransmitted through the atmosphere and then it is captured by the sensing systems, right? You interact with the target. So once that energy makes its way to the target through the atmosphere, it interacts with the target depending on the properties of both the target and the radiation. So then the next step are the sensing products, or what you do is you record that energy by the sensor. Sensing systems will sense that energy and it will save it. So what you basically sense, you obtain that data, right? So after that energy has been scattered or emitted from the target, we require a sensor to collect and record the electromagnetic radiation, right? So that it is recorded. Then after that, it is interpreted and analyzed. So that processed image is interpreted visually or digitally or electronically to extract information about the target which was illuminated. Then comes the information products or the final applications. So that final element of the remote sensing process is achieved when we apply the information we have been able to extract from the imagery about the target in order to better understand it, reveal new information, or assist in solving a particular problem. Then it comes to the end user. So this is the basic steps in acquiring and using remote sensing data. So as I mentioned, the different energy sources you have to consider. So the main energy propagation that we consider in remote sensing is the electromagnetic energy. So visible light, radio waves, UV rays, heat, X-rays, microwaves, all these are different wavelengths or different components of the electromagnetic spectra or the electromagnetic energy range, right? So this radiates according to the basic wave theory. So electromagnetic energy travels in a harmonic sinusoidal fashion at the velocity of light. What is the velocity of light? 3 into 10 power 8, or 2.998 is the actual value. 2.998 into 10 power 8 meter per second is the speed. So as I mentioned earlier, so the first requirement of remote sensing was to have a energy source to illuminate the target, right? Unless the sensed energy is being emitted by the target itself, like a mobile flash, right? If you're not using your flash, you will need natural light to do that, right, for you. So the energy source is required to illuminate the target, and that energy which is used to illuminate the target is in the form of an electromagnetic radiation. So all electromagnetic radiations has fundamental properties, and it behaves in predictable ways according to the basics of wave theory, as I mentioned. So electromagnetic radiation, there are two components. You have a sinusoidal electric wave and a similar magnetic wave, which are perpendicular to each other in the direction of propagation, as you can see here. You can see here. This is the direction of propagation. You have a combination of magnetic field and electric field perpendicular to each other, right? So this is the basic structure of an electromagnetic wave. So it consists of the electrical field which varies in magnitude in a direction perpendicular to the direction in which the radiation is traveling, as you can see here, and a magnetic field, as you can see here, and a magnetic field oriented at right angles to the electric field. So both these fields travel simultaneously at the speed of light, right? So basically you need to understand two characteristics of an electromagnetic radiation for understanding remote sensing. So that those two characteristics, one is shown here, one is wavelength and another one is frequency. So what is wavelength? Distance between two crusts or troughs. So it is basically the length of one wave cycle, isn't it? It is the length of, you can see here, length of one wave cycle, either from two troughs or from two crests. The distance between two troughs or two crests, isn't it? As you can see here, from here to here. So it is a length of one wave cycle. So it can be measured as the distance between successive wave crests or successive wave troughs, right? So it is represented as lambda. So what will be the unit of wavelength? So here we are talking about electromagnetic wave. So we are talking about this wavelength in terms of micrometers or nanometers. So it is basically a distance measure, right? It's basically a distance measure. So it's a unit when it measured along the electromagnetic spectrum, we can consider micrometers or meters or nanometers or anything, any distance measure. All right. So next comes frequency. What is frequency? This is the number of cycles of a wave passing a fixed point per unit of time, right? So what is the unit of frequency? Hertz, right? So hertz, it is equivalent to 1 cycle per second, right? Correct, 1 cycle per second. So it is represented as hertz, which is actually 1 by second. So number of cycles per second passing through a fixed point is the frequency of the wave. So these two characteristics are intertwined for an electromagnetic spectra, and these two are used to define the electromagnetic spectra, right? So as I mentioned, these two components of electromagnetic spectra travel simultaneously in the propagation direction. As you can see here, perpendicular to each other, they travel at the speed of light. That's 2.998 into 10 power 8 meter per second. So they obey the general equation of light, which is C is equal to lambda F. So here you can see C is equal to lambda F. So lambda is equal to C by F. So you can see that lambda and F are inversely related, right? Wavelength and frequency are inversely related to each other. So that means the shorter the wavelength, the higher the frequency, and longer the wavelength, lower the frequency, right? So understanding the characteristics of electromagnetic radiation in terms of their wavelength and frequency is very much necessary to understand the information to be extracted from remote sensing data. So let us next see how to categorize electromagnetic radiation. Before that, let us just discuss particle theory once. So electromagnetic radiation, it was found that electromagnetic radiation, it is composed of many discrete units called the photons or quanta. So energy of a quantum is given by Q is equal to H into F joules, where H is the Planck's constant, right? And F is the frequency. So Q is equal to HF, and we know that F is equal to C by lambda from the general equation that we saw. C is equal to lambda F is equal to C by lambda. So Q basically equal to HC by lambda. So this is my particle theory. So it means that the energy of the quanta Q, it is inversely proportional to the wavelength. So higher the wavelength, lower the energy, higher the energy, lower the wavelength. So longer the wavelength, lower the energy content, right? So Q is equal to Hc by lambda. This is explained by the particle theory using the Planck's constant. So keeping this in mind, let us now explore the electromagnetic spectra. So you can see here increasing wavelength in this direction. And according to the particle theory, larger the wavelength, lower the energy. So increasing energy is in this direction, increasing wavelength is in this direction. What about the frequency? In which direction will be the frequency increasing? What is the connection between frequency and wavelength? Inversely proportional. What is the connection between energy and frequency? Proportional, right? Right. So you can see here the wavelength is increasing in this direction. 10 power minus 11 to 10 power 3 wavelength is marked here, and frequency 10 power 4 to 10 power 20 is marked here, right? So wavelength and frequency it's inversely proportional, right? So this band you can see here. This is basically the electromagnetic spectra, and you can see here this is only a very thin band of wavelength that we can actually observe. This is the visible spectra, right? This is the only wavelengths that the human eye can possibly perceive, right? So looking at this figure, let us try to discuss the various components of the electromagnetic spectra. So it ranges from short wavelengths. You can see here it ranges from short wavelengths, including the gamma rays, X-rays, etc., to the longer wavelengths, which includes the microwaves and the broadcast radio waves, right? So out of this, several wavelengths are used for remote sensing. Different sensors are designed to absorb electromagnetic radiation in the various wavelengths for acquiring data, right? So most purposes, the ultraviolet or UV portion of the spectrum has the shortest wavelengths, which are practical for remote sensing. You can see here the UV spectra. So this is beyond the violet portion of the visible wavelength, so that is why it is called the ultraviolet. So some of the Earth's features, materials, or Earth's surface features or Earth's materials, uh, mainly rocks and minerals, they emit visible light when it is illuminated by UV radiation. So UV radiation has a lot of applications for applications in remote sensing, because many of the Earth's features, especially rocks and minerals, they emit visible light or they fluoresce. They keep that energy and they will radiate it at a later stage. So this can be absorbed by ultraviolet radiation. So what you will do is you can develop sensors which records wavelengths in this range, in the ultraviolet range, and use that for remote sensing, specific remote sensing purposes, right? So the light which the eye can see, or our remote sensors, the eyes. So what we can detect is part of the visible spectrum here. So we can see that here it is ranging from about 4 to 0.4 to 0.7 micrometers, or 400 to 700, or up to 750 nanometers. So the longest visible wavelength is red. As you can see here, the longest wavelength in the visible spectrum is red, and the shortest is violet, as you can see here. So common wavelengths of what we perceive as particular colors from the visible portion of the spectrum are violet, blue, green, yellow, orange, red, etc. Right? So what are primary colors? Blue, green, and red. Right? You can see the shortest wavelength of that three is blue, then comes green, then comes red. Right? So they are called primary colors because no single primary color can be created from the other two. You cannot create green from blue and red. You cannot create blue from green and red. So all the other colors can be created as a combination of these three primary colors. That's why they are called primary colors. So what color do you think sunlight is? It's some uniform homogeneous color, right? We can't we don't know what exact color it is, right? It's actually composed of different wavelengths of radiation in various ranges. Have you seen that prism experiment? If you use a prism, or maybe the rainbow, what happens there? The electromagnetic radiation is scattered, right, through a prism. Have you seen that through maybe a glass? When the sunlight passes, it splits into its component colors. You might have seen, right? Or the rainbow. It's basically the sun's energy has a lot of wavelength energy in it, at different wavelengths, and when it is scattered, what we see is only the visible spectra. The basic 7 colors is what we see. VIBGYOR is what we see, right? Yeah. Then coming to the next portion of the spectrum of interest is my infrared radiation region. So it covers from about 0.7 to 100 micrometers. So you can see that it is about 100 times as wide as the visible portion. right? So this is basically divided into two categories. One is the reflected infrared and another one is the emitted or thermal infrared. So radiation in the reflected infrared region is used for remote sensing purposes, similar to that of the visible portion. And the thermal IR region, it is pretty different, which is of longer wavelengths. So the thermal IR region is this energy is the radiation that is emitted from the Earth's surface in the form of heat. Features on the Earth's surface, they will store some energy and they will release it at a later stage. It will emit this energy, right? So that is sensed by the thermal IR. So that the thermal IR covers wavelengths from approximately 3 to 3 micrometer to about 100 micrometer. Have you seen a thermal image? Thermal imaging, you might have seen in many movies and all, no? Thermal imaging. The Predator movie, most of you might have seen how the Predator sees you, right? Yes, I am sure most of you have seen a thermal image, right? So that thermal image is sensed by electromagnetic sensors or remote sensors which operate in the wavelength range of 3 micrometer to 100 micrometers. All right. Then comes the microwave region, which is of very much interest to us. I will tell you why microwave remote sensing is very important at a later stage. But first, let us see that the microwaves, it comes after the infrared or reflected infrared or the thermal infrared. It has higher wavelength than that, ranges from about 1 millimeter to 1 meter. So this covers the longest wavelengths which are used for remote sensing. And the shorter wavelengths have properties similar to that of thermal infrared region, while the longer wavelengths approach the wavelengths used for radio broadcast. So this range, about 1 millimeter to 1 meter, also has very wide applications in remote sensing. We will discuss why soon, why it is more important. So here we can see the spectral luminous efficiency for the human eye. You can see what wavelengths, the intensity of luminous, the luminous efficiency for the human eye. You can see the most bright you will observe as about 560 nm of wavelength, and that keeps decreasing, and it keeps decreasing here, and beyond about 400 you cannot see, and beyond about 700 you cannot see. This is the only visible spectrum of the electromagnetic spectrum visible to the human eye. So the spectral sensitivity of the human eye is about 0.38 to 0.7 micrometers. So next we will discuss the Stefan-Boltzmann's law. According to the Stefan-Boltzmann's law, all matter at temperature above absolute zero continuously emits electromagnetic radiation. What is absolute zero temperature? 0 Kelvin. So anything above 0 Kelvin emits some electromagnetic radiation, right? Anything about 0 Kelvin emits some electromagnetic radiation, and that energy that particular object radiates can be represented as a function of its surface temperature, all right, which is expressed by the Stefan-Boltzmann's law. So M is equal to sigma T power 4. It's directly proportional, where M is the total radiant excitance from the material surface, or the energy exiting from the material surface. Total radiant excitance from the material surface, W per meter square. So it is equal to sigma into T power 4, where sigma is the Stefan-Boltzmann's constant and T is the absolute temperature of the emitting material. So you can see that the total radiant excitance or energy emitted from us from an object is proportional to the power 4 of the absolute temperature of the emitting material. So you can see that with every degree rise in the temperature, there will be a drastic increase in the total radiant excitance from the material surface, right? So this was developed for all black bodies. So what is a black body? Anyone know what is a black body? Black body, it's actually a hypothetical ideal radiator, right? It's an ideal radiator. That means it absorbs all the energy incident on it and it re-emits all the energy that was absorbed, right? Whatever energy influx will be same as the total energy outflux. That is a black body. So it is a hypothetical ideal radiator. That means it completely absorbs all the energy upon it and re-emits all that energy incident upon it. All right. So this was developed considering a black body, but the applications for the general visible spectra or all the other wavelength, it is very important for us. So here you can see the spectral radiant excitance M. As I mentioned earlier, M is equal to, what is the equation of M according to Stefan-Boltzmann's law? M is equal to sigma into M is equal to sigma into T power 4, right? So the area under each of these curves represents the total radiant excitance. All right. So these graphs are for different surface temperatures at different kelvins. You can see what will be the surface temperature of the Earth for an average range of the Earth's surface temperature 26 to 27 degrees. So here you can see 300 Kelvin, right? Kelvin to Celsius, how will you convert? Plus 273, isn't it? So something around 300 Kelvin is the black body radiation curve for the Earth's ambient temperature. You can see here. So that happens at a wavelength range of something about 4 to 51. You can see here, isn't it? So is that in the visible spectrum? Can you see that? The energy radiating from the Earth's surface. Can you see that? No, right? But here you can see black body radiation curve at incandescent lamp temperature. An incandescent lamp. Will you be able to see that lamp, which is emitting some form of an energy? Yes, right? You can see that. Then for about 6000 Kelvin is the surface temperature of the sun. And if you plot the total radiant excitance for the sun, you can see this. Some part of it is covered by the visible radiant energy band. You can see here. Some of it is covered in the visible wavelength, isn't it? So this is your wavelength. And this is your spectral radiant excitance, and these graphs show the spectral radiant excitance for various surface temperature according to the Stefan-Boltzmann's law. So here you can see that the energy emitted by the sun, you can observe, of course, some energy emitted by a incandescent lamp that will be about 3000 Kelvin that you can observe, and some of these you can observe. So the surface temperature has to be pretty high so that you can observe its energy. So can you mention any other situation where you observe an item due to the energy it emits when it is very hot? Any other example other than the reflected energy from the illuminating source, which is the sun? Sometimes some materials, when they are very hot, they emit this energy and you can perceive it with your eyes. Any other example can you mention? So the surface temperature has to be very high, as you can see here. For it to be in the visible range, it has to be definitely above 1000 Kelvin, right? So can you mention one or two examples which you can see? Heated metal, right? So when you heat a iron, what happens? When you heat iron, what happens? What range its color changes from? Do you know? First it will become red, right? Then slowly it changes to yellow, then blue shade, then finally it will become purely white, and then late after that you won't be able to perceive that emitted energy, right? Because the wavelength keeps on decreasing, right? Wavelength keeps on decreasing. The energy it contains, it keeps on increasing or decreasing. You're keeping on heating it. The energy of that material keeps on increasing, and energy and wavelengths are, how are they connected? Inversely proportional, isn't it? That is why it changes from red, which is of the highest wavelength, and it slightly changes to blue to white, and then you cannot see the further, you cannot, with your eyes you cannot perceive that energy, right? You can see the wavelength keeps on decreasing with an increase in energy. You keep on heating it, that color changes, right? So here if you look at this, the sun produces 41% of its energy. You can see here blue, green, red. Sun produces 41% of its energy in the visible region, and the rest 59% are in the wavelengths shorter than 0.4 micrometer, as you can see here, and longer than 0.7 micrometer. So this was the radiant excitance curve that we saw here, 6000 Kelvin. This one, same thing I have shown here. All right, same thing I've shown here. So if you look at the radiant excitance of the sun, only 41% of its energy is in the visible range. So the rest of it is in the shorter than 0.4 micrometer and longer than 0.7 micrometer range. So we can consider different remote sensing detectors or different sensors which can be made to energy sensitive in the non-visible regions of the spectrum for different purposes, as you can see here. So that you don't need a external source to illuminate only what you can perceive with your eyes is only in this range, and other than that there is electromagnetic energy and radiation, but you cannot see that. So what you can do is you can use the sun's natural illumination source, and you can generate, you can design and develop sensors for these different ranges, different wavelength ranges, and you can use those sensors in remote sensing satellites or drones or anything like that to sense the energy at different wavelengths, right? So you can, what I mean to say is that the sun's reflected energy, what we perceive with our eyes, is not the only wavelengths that we can actually use for various data collection purposes. That is, comes to only 41% of the sun's energy which is reflected. The rest 59% we can design various remote sensors to observe energy in these different wavelengths. Clear? Next comes the Wien's displacement law, pretty simple equation. So the dominant wavelength lambda at which a black body radiation curve reaches a maximum. So here you can see what is the dominant wavelength. So that is the wavelength at which black body radiation curve reaches its maximum, and it is related to its temperature. So you can see here. So what is the dominant wavelength of the Earth? What will be the dominant wavelength of Earth? Something about between 9 to 10, isn't it? You can see for the Earth's temperature, the black body radiation curve for the Earth's temperature, you can see 300 Kelvin. That line you can see 300 Kelvin. That is for the Earth's surface features, right? Because we discussed earlier, right? Earth's ambient temperature we consider it as 27 degrees. So 27 plus 273, it is 300 Kelvin. You can see that curve, the second curve from the bottom. The peak of that particular curve is considered as the dominant wavelength. The wavelength at which the peak of that curve occurs is called the dominant wavelength. So 9.8 micrometer is the dominant wavelength of the Earth's surface features. Can we see that actually? 9.8 micrometer, can we see that wavelength? No, right? We cannot see that. That's why we cannot observe, if you go to moon and if you observe Earth from moon, the Earth's energy that is radiated from the Earth, we cannot see that. What we see is the reflected light from the sun, isn't it? That is why half of the, even the moon, half of it observes dark, right? When we see from here, or when we observe the Earth from the moon, half of the Earth observes as dark because only the other half shows some reflected energy, other half is emitting some energy, but we cannot perceive that because that energy is emitted at a wavelength of 9.8 micrometer. Clear? So we cannot perceive that, but we can design a remote sensing sensor which can actually capture wavelength that particular range. If you had such a sensor, if your eye had capacity to sense up to 10 micrometer, then you can see the Earth, the dark side of the Earth also you might have been able to see. According to Wien's displacement law, there is an inverse relationship between the wavelength of the peak of the emission of a black body and its temperature. So lambda m, which is the wavelength of the maximum spectral radiant excitance, which is my dominant wavelength, it will be equal to B by T, where B is Wien's displacement constant, 2898 micrometer Kelvin. It is the Wien's displacement constant, and divided by T is the temperature in kelvins. So lambda m is equal to B by T. That is Wien's displacement law, which basically defines your dominant wavelength. So that is the wavelength at which a black body radiation curve reaches a maximum related to its temperature. Here you can see again the same curve what we saw earlier, intensity or radiant excitance versus wavelength. You can see here for 6000 Kelvin, this is something for the sun. Right, this is 300 Kelvin, that's for the Earth. Right, so here you can see lambda max or the dominant wavelength, you can see here. Right, so for a black body, the wavelength at which the maximum spectral radiant excitance occurs, so that varies inversely with the black body's absolute temperature. Right, we already saw that. Right, so the wavelength at which maximum spectral radiant excitance occurs, it varies inversely with the black body's absolute temperature. We saw that as well, right? These two basic laws we saw already. Lambda max is equal to B by T, and m was equal to sigma into T power 4. Wien's displacement law and Stefan-Boltzmann's law we already. So this is basically observed in the heating of iron as we discussed earlier. So as it gets hotter, it glows and the color changes to shorter wavelengths. From dull red to orange to yellow to white, it will vary, right? Similarly, the Earth's ambient temperature, it is about 300 Kelvin as I mentioned. So the maximum spectral radiant excitance of the Earth's features occurs around 9.7 to 9.8 micrometers. So that falls in the thermal infrared, isn't it? So here we saw that peak, it happens something around about 10 micrometer, right? For the Earth's surface features, it happens something around 10 micrometer, right? So that falls in the thermal infrared region. So if you have a thermal infrared sensor and you go to space and try to photograph the Earth, you can see the dark of the Earth as well, isn't it? That is the basic concept here. So that falls in the thermal infrared range. So the dominant wavelength is 9.7 micrometer for the Earth's surface features. So this cannot be observed or photographed, but it can be sensed using thermal devices like radiometers and other scanners. So there is a dividing line between reflected and emitted infrared. Wavelength is approximately 3 micrometer, below which the reflected energy dominates and above which the emitted energy prevails. So far what we discussed is the ideal concept for a black body radiation. So is the Earth an ideal black body? No, Earth is not an ideal black body. So these concepts can be used to define these parameters and it can be used to explain the concept. It's 100% practical for a black body radiation, but it is not exactly the condition for the various features that we actually observe. So what you will perceive or what you will sense in those cases will be the emitted or reflected infrared radiation rather than the black body radiation. What you will observe in those conditions will be the emitted or reflected wavelengths, right? Because you have an external source to illuminate it and some of the energy will be, suppose the external source of course that I mentioned here is obviously the sun. So some of the energy from the sun is emitted, some of the energy is stored by the earth and some of that energy is released later, it is emitted, or some of the energy is reflected from the surface. So that is what we actually sense. Is that clear? So some energy is stored and emitted, some energy is reflected. Correct? The whole energy that falls on an object, it is either emitted, either absorbed or reflected, right? Isn't it? An energy that falls on a body, it is either reflected or it is absorbed. Yes, correct. And that absorbed energy at a later stage it is emitted, right? Maybe then itself or at a later stage it is emitted. Yes or no? Fluorescent objects you have seen. Have you seen fluorescent objects? It will absorb this energy, it will store that energy, and at a later stage, when you switch off the light, you can see that these items glow. Yes or no? Your watch dials, you might have seen, your alarm clock's dials, you might have seen a fluorescent object, a fluorescent substance you might have seen. Yeah, so what does that do actually? It will absorb the energy and it will emit at a very slow rate. Yes or no? So that is what happens here. You can either store and emit that energy later or you can reflect that energy. So this reflected infrared and the emitted infrared are in different ranges as I mentioned earlier. The lower wavelengths are the reflected IR and the higher wavelengths are the thermal IR, which is basically the emitted and reflected IR. So you can develop sensors for recording or obtaining information in those wavelengths higher than our red infrared above 700 micron. That energy or those wavelengths you can design sensors so you can visualize or you can capture energy variations or energy spectra, or you can basically capture the data at those wavelengths, right? So this was idealized using the concept of the black body radiation, and the concept behind it is pretty much same, but the wavelengths slightly varies when it is in the reflected or emitted wavelength range. So here you can see this is a thermal image. Predator movie, if you have seen, you might have seen this. The Predator sees Arnold Schwarzenegger like this, isn't it? Do you remember? Those who have seen the movie Predator might have seen this. So what his vision is in the
Thermal IR range. He can see in the dark, isn't it? You can see in the dark. If you have a thermal sensor, you can see this in the. You can see in the dark. Yes or no? If you had a thermal sensor, you can see in the dark. Why is that? So above absolute zero temperature, all bodies emit some radiation, emit or reflect some radiation. So this is emitted radiation because there is nothing to reflect at night, isn't it? So they emit some radiation at different temperature. If anything above absolute zero, that emits some emits some energy. But can you actually visualize it? Can you see that actually? We cannot see, right? If it was in the visible wavelength range, then we could have seen that, but no. You can sense that using specially designed spectrometers or thermal sensors if that wavelength is in the uh, thermal IR range. You can use spectrometers or thermal IRs to actually sense those images. So if our eye had a capacity to observe in the thermal infrared range, we would have been able to see people like this at night. Yes or no? Do you understand the concept now? Our eye cannot see that, but we can design sensors to capture data like this. So this is the basic concept of remote sensing and electromagnetic spectra. So you can design remote sensing sensors for various purposes to capture the emitted or radiated energy at various wavelengths for different applications. Is that clear?